Hello, everyone. This is day 3 of the 50 days of tutelage. You're welcome once again. I remain your tutor, Isaac Adeniro. And today we are doing chemistry. We're talking about the atomic structure. Atomic structure. But before we talk about the structure of an atom, let's quickly talk about what an atom is. I know there's a common definition which says atom is the smallest indivisible part of an element. And once you give that definition, you'll be like, oh wow, I just made a delivery. I would want us to jettison that definition for now. And then for atomic theory, there's so many things to explain about that definition. But the proper definition I want us to work with is that an atom is the smallest unit of an element that still retains its chemical properties. So take note of that. An atom is the smallest unit of an element which still retains the chemical property of that element. By the way, if you don't have your notes with you right now, you are wrong. Go and get your notes so that you can jot things down. Now, let's talk about the structure of an atom. We're going to be dividing the structure of an atom into two major parts. Of course, there are other parts of this structure, but we're going to be using two major parts. And there's a part that is internal and another part that is external. So I'm going to start with the internal part. The internal part is known as the nucleus. The internal part is known as the what? As the nucleus. And then we have the external part. The external part is known as the shell. So let me draw that here. So we have the nucleus as the internal part. Let me put this in. Yeah. Don't mind my diagram. It might be a little bit funny. Yeah. So the nucleus is the internal part. Let me place that more at the center. And we have the shell. The shell is the external part. So in the nucleus, which is actually the place where the mass of an atom is concentrated. So you can regard all this shell like this now, the mass is actually negligible compared to what the entire mass of the atom is. So this is where the mass of the object of the atom is well concentrated. Take note of that first. At the nucleus is where the mass is well concentrated. And there are two guys there. We have what we call subatomic particles. Subatomic particles. That is inside your atom, another atom there. Yeah, just take that like that. So we have subatomic particles. Anyways, they're not atom. I'm just like kidding. Now we have proton, we have neutron, and we have electrons. These three guys are subatomic particles. At least the one that we'll be discussing in this class. Now, proton and neutrons, they are present in the nucleus. They are present in the what? In the nucleus, and that's why we call them the nucleon element. With the nucleon element, so they are present in the nucleus. Now, the proton is positively charged. The proton is so note proton is positively charged. Neutron, you would think that, oh, P for positive, then neutron should be negatively charged. No, neutron does not have any charge, no charge. That is, it is neutral. So, which means that the net charge at the nucleus is going to be a positive charge, a positively charged nucleus. The shell is where we have what we call the electrons. These electrons are negatively charged. And like I've said, the mass of an atom is concentrated at the nucleus. So therefore, the mass of electrons, it is very, very negligible. Mass of electrons is very, very negligible. So the mass of proton and neutron are the one that actually determines the mass of an atom. So that's the first part of atomic structure. Dividing them into two, we have the nucleus and we have the shell. The nucleus, what do we find there? We have the proton and the neutron. There are the nucleus, and then the electrons, they are always found on the shell of an atom. Now, going further, before we move into some other things, there are some, like I said, that the mass number of an atom is determined by, is actually concentrated at the nucleus. So therefore, the mass number of an atom, or let's say the mass number of an element, is always the sum of the proton plus the neutron. Sum of the proton plus the neutron. Now, here's what I want you to note. Before we begin to go into some other types of substances, we are talking about a neutral atom here. And one thing about a neutral atom is that the atomic number is also the same thing as the number of proton. So which implies that when you pick any random element and you get their number in the periodic table, that is, oh, is it element number 19, element number 31, element number 40? Now, whatever number that you get is their atomic number. That is their number in the periodic table. This number also corresponds to the number of proton that they will have. So atomic number is the same thing as what? Proton number. Now, however, the neutron number can vary. In fact, there's another concept we will discuss in the course of this class, which I don't want to talk about now. Neutron number is what determines this variation in this concept that I will discuss later. So back to number of proton. But I want to quickly discuss something about electrons. You see, when you have a neutral atom, the number of protons and the number of electrons are always the same. So if I pick a random atom and then the number of proton there is 19, that implies that this neutral atom will also have 19 electrons. So this is why a neutral atom is neutral, because the amount of positive charge that it has is also the same as the amount of negative charge that it has. So these two guys equally neutralize each other. So that is for a neutral atom. So don't forget, we are talking about the structure of an atom. However, this structure I've given now is just like more like a generic structure, the nucleus and the shell. The shell can be more than one. The shell can be more than one. And for the shell to be more than one, so we have what we call energy levels. We have what we call energy levels. Now, before I go into energy levels, the concept I was trying to discuss earlier about the variation of the number of neutrons is the concept of isotopy. Isotopy. Isotopy is just a phenomenon that talks about the fact that you have guys that have the same element, they have the same atomic number, but they have different mass number. They have the same atomic number but different mass number. So like I've said, what makes an element is the unique number of atoms, the unique number of protons. So if there are 19 protons, the atomic number is 19 rather, then you have 19 protons. However, the neutron number can change. The neutron number can change, which is why the mass of an element can actually vary. That is why you can have sometimes the element chlorine. Chlorine has an atomic number of 17. You can have chlorine 35 and you can also have chlorine 37. Now, these two guys, they are chlorine as an element. However, they have 17 as their atomic number. That is, the number of proton in these two guys is also 17. But this chlorine, the mass number is 35, and the one on the right, the mass number is 37. And what this implies is that this guy, the number of neutron there will be 37 minus 17, which will be 20. The number of neutron here will be 35 minus 17, which will be 18. And the implication of this is that they do not have the same number of neutron because they do not have the same mass number. These two guys are known as isotopes. Isotopes. So the phenomenon is known as isotopy. Another one is the hydrogen. So you have hydrogen. This is the proton. Then you have another one. You have deuterium. And then you have another one. This is tritium. These are three isotopes of hydrogen: the proton, the deuterium, and the what? And the tritium. These are isotopes. So isotopes, they have the same atomic number. That is, they have the same number of protons, but their neutron number varies, which in turn makes their mass number to also vary as well. Now, let's go further in this whole thing. The shells, like I said, most times elements don't have just one shell. We'll talk about this more when we discuss periodic table. If they have more than one shell, there's a way we arrange electrons in these shells. And then these shells, they have what we call energy levels. So let's say this is the nucleus. So we can have a first shell here. We can have a second shell here. We can have a third shell here. In fact, we can have a fourth shell here. I'm going to stop at the fourth shell. Now, these shells, they are called energy levels. And they start with, we have the energy level here. This one is called K. this one is L, this one is M, and this one is N. Corresponding number to them, K is 1, energy level 1, this is energy level 2, and this is energy level 3, and N is energy level 4. By the way, this K, whatever electrons that are present there are strongly attached to the nucleus, and it will take so much energy for you to remove them. This is a concept that we'll discuss later. But how do we now arrange electrons? Don't forget, like I said, in a neutral atom, the atomic number, that is the number of proton, is the same thing as the number of electron as well. So if, let's say, I'm picking an element that has, let's say, 18 as the atomic number, that means that it will also have 18 electrons. So how do I arrange 18 electrons around these shells? Do I just say, oh, 18, how many do I have here? 1, 2, 3, 4. 18 divided by 4. 4 will not quickly go it. 4 will go there, that's like around 4.5. So I can just split it and just say, okay, let me put 4, 4, 4, 4 here, and then let me distribute. No, you don't do that. There is actually a way we arrange these guys. The first thing you need to know is that the K shell can hold only the maximum number of electrons, which is 2. The L shell can hold a maximum number of electrons, which is 8. The M shell can hold a maximum number of electrons, which is 18. And the N shell, now, by the way, there's a formula we use to get all these things. The formula is simply 2n raised to power 2. So in this case, n is this energy level number. So we have 1, we have 2, we have 3, we have 4. So if you square 1, 1 square is 1, 1 times 2 is 2. If you square 2, 2 square is 4, 4 times 2, you have 8. If you square 3, 3 squared is 9, 9 times 2, you have 18. And so 4 square is what? 16. 16 times 2, that is going to be 32. Now, this I've listed here is the maximum number of electrons that each of these guys can hold. However, so what happened is that when we are filling this electron, that is these 18 electrons in each of these shells, we start from the innermost guy. And we maximally fill this shell before we go to the next shell. However, there's a special rule for when you have the M shell. The M shell, even though it can maximally contain 18 electrons, we do not fill the entire 18 for the first 20 elements. This, I'm going to be explaining this when I'm talking about a proper electronic, I will talk about electronic configuration in another video entirely. So I'm going to explain why we say for the first 20 elements, we should not fill the 18 electron completely. Instead, we are only going to be assuming that it can only hold 8 electrons maximally. So that implies that, so let me fill these 18 electrons now. The K shell can only contain 2 electrons maximally. So I can say put 2 electrons here. After the 2 electrons, what will I have left? I will have 16 electrons left. The next shell can hold 8 electrons. So let me distribute that. That will be 1, 2, 3, 4, 5, 6, 7, and 8. So I'm done with 8. How many electrons do I have left? 8 electrons. Now, the next shell, which is what? M shell. This M shell is said to be able to hold 8 electrons maximally. So that implies that this can also hold 8 electrons. And with this, I am done with whatever thing I'm filling. I don't need to go to N shell because there's no electron left again. So that is for the first 20 elements. So let's do for something else. Let's do for chlorine that I just said now. So chlorine has what atomic number? The atomic number of chlorine is 17. So therefore, chlorine will also have 17 electrons. So let's say this right here is the nucleus. So around it, we have the shells. That's the K shell, the L shell, and the M shell. So let's see. We'll start from the innermost shell. From what we have known already, the maximum number of electrons that can be in the innermost shell is 2. So we have 1, 2. So after 2 is gone, what do we have left? 15 electrons. Then the next one, which is the L shell, can hold 8. So we have 1, 2, 3, 4, 5, 6, 7, and 8. So after 8 out of 15, what we have left is 7 electrons. And then so we feel 1, 2, 3, 4, 5, 6, and what? And 7. So this is chlorine. This is the structure of chlorine. By the way, there are also what we call subshell, but I'm not going to be talking about that very much now. I'll talk about that when I'm discussing the electronic configuration in the video for electronic configuration. So let's continue with this now. Let's do one more. Let's say we want to do for element number 19. So permit me to just use this. I don't want to draw another one. So if you have 19 electrons, so you fill 2 first, you get 17 left. You fill 8 out of 17. What you have left is going to be 9 electrons. So you fill 2, 2 is gone, 8 is gone, so you have 9 left. And this place now, you fill 8. So after you fill 8, you still have 1 electron left. 1 electron left after you fill. That means that 1 more shell is going to be required here, and the 1 shell is going to go like this, and then you have just 1 electron at this last shell. So that is how you draw the structure of an atom. Now let's move to the electronic configuration. Now, what is electronic configuration? It's simply the way we arrange electrons in an atom. Like we have already said here, we've already discovered that like electrons are found around the shell. So we place them around the shell from one energy level to the other, from K to the L shell to the M shell and to the N shell. However, there are this shell of a thing is like a country. And if you say you're looking for someone and you give a description that, oh, this person lives in a country, let's say for instance now, they live in Nigeria. So you can't just come to Nigeria randomly and say, oh, this person lives in Nigeria, so you just come to Nigeria and you just find them in that place. If they are living in Nigeria, that is a country, what state are they living in? So you have a country, then you can talk about states. Now, given the states where they live in that country, then you have the higher probability of finding them in that state than it is finding them in that country. So shells are like country. So state is what we call subshell. So there's something also called subshell. I'm going to discuss this thing in detail. And state is also kind of too big for you to find someone. So the best place, what you can describe is, let's say you don't want to give the exact house of that person. You don't know the person's house address. Then you can talk about the street. So from country to state and to the what? To the exact street where they are staying. Now you do not want to describe the house of the person, but you want to describe the street. There's tendency that if you stay on the street where they are, if you mount maybe one end of the street where they are living, and if you mount it for the next, let's say, couple of days, 7 to 10 days, you just stay there watching out for who is going and who is coming, you are going to find this person one day. You might stay for another 10 days. It doesn't really matter. So what I'm trying to say is that the probability of finding electrons in an atom increases as you move from the country, which is the shell, and you move to the state, which is the subshell, and you go to the street, which is called the orbital. So the atom also have this shell, also have what we call subshell, and inside subshell you also have what we call orbitals. And as you begin to go down, you have increased probability of finding electrons in that particular region. So electrons are found around the shell. However, they are closely placed in the subshell, and there's higher probability of finding them in the orbitals. But the orbitals is it belongs to the subshell, and the subshell belongs to the what? It belongs to the shell. So we are still saying the same thing if we say electrons are found around the shell, but there is more detail when we say electrons are found in the orbitals. We've discussed about the shells. We have the KLMN. Now the KLMN, we say K is the first energy level, then we go to the second one, to the third one, to the fourth one as well. Now we have subshell as well. Now the subshell that we're going to be talking about for the purpose of this class are the subshell S, P, D, and F. Subshell S, P, D, and F. Now, for this subshell, we can have a total number of orbitals of 1 in the S subshell. So the S subshell has a total number of 1 orbital, and the P has a total number of 3 orbitals. The D has a total number of 5 orbitals, and F has a total number of 7 orbitals. So I want you to follow that very well. Now, S, 1 orbital, P, 3 orbitals, D, 5 orbitals, and F, you have 7 orbitals. One more thing, each orbital can only hold 2 electrons maximally. Each electron can only hold each orbital can only hold 2 electrons maximally. So let's run through this again. We have the subshell. These guys are the subshell. These number of orbitals. This is number of orbitals. Now, because each one can only hold 2 electrons for every 1 orbital, 2 electrons. 1 orbital, 2 electrons. Take note of that. So that implies that if S has just 1 orbital, therefore, number of electrons now. So if S has only 1 orbital, that means that the maximum number of electrons that S can hold will be 2 times 1, which is 2. P has 3 orbitals. That means that the maximum number of electrons that it can hold will be 6 electrons. And for D, if it has 5 orbitals, that implies that the maximum number of electrons it can hold is going to be 5 times 2, which is going to be 10. And for F, the maximum number of electrons it can hold is going to be 14. So I believe you are getting the build-up one after the other. Now, for this K shell, K element, I'm going back to the K element shell now. The number, their energy level, the number that corresponds to their energy level, also determine the number of subshell that they can have. Meaning that the K shell can only have 1 subshell. L shell can only have 2 subshell. M shell can only have 3 subshell, and N shell can only have 4 subshells. And so let's see how we can identify these subshells. So for example, you have the K shell. The K shell can only have 1 subshell, and that subshell is described using 2 things. First of all, we are always going to be proceeding from the S to the F shell, and the number, which is K corresponds to the energy level 1, L corresponds to energy level 2, M corresponds to energy level 3, and 4 corresponds to energy level N. And like I have explained already, each of these will always have a number of subshells that corresponds to the number that corresponds to their energy level. Now, so 1 subshell, and that is going to pick just S only. But to identify whose subshell it is, we say 1S. So when we get to the second one now, this L is going to have 2 subshells. But to identify it, we'll always put 2 behind any of the subshell. So we have S now, so this is going to be 2S. So we have 2S, but since we can have 2 of them, we can still get to P. That is going to be what? 2P. Now you can guess what is going to be for M like that. M is going to have 3 all through. So we have 3S, we have 3P, but this time around we can also get to what? 3D. Now for N now, we have 4S, we have 4P, we have 4D, and we can also have 4F. So you can see the trend. The trend is their energy level, the number that corresponds to their energy level, also gives the number of subshell that they can take on. And before we write this subshell, we always put the number of their energy level just before them. 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f. So if we have a fifth shell now, that implies that we're going to have something like 5s, 5p, 5d, 5f, and whatever it is that follows in the fifth place. But I don't want to go beyond this in this particular video. Now that we have established some of these things, we've talked about shell, we've talked about subshell, and we've talked about orbitals. Now let's quickly go through the 3 rules before we can write electronic configuration of any element or of any atom, whichever one we want to do. The first one is what we call the Bohr's principle. I may not be pronouncing that name very well, so but let me write it. We have the Bohr's principle. Now, what does this principle state? It simply tells us that electrons fuse lowest energy orbitals first before they go to higher orbitals. So therefore, this whole thing that we have been able to map here, they will represent our orbitals. And how do we know which one is a lower orbital before we can go to the higher orbital? So what we do is that we use the diagonal rule. All we have to do is to draw a diagonal that is coming from the right to the left, dropping from right to the left. So this is what I mean by that. So this is the first diagonal. This is the second diagonal. This is the third diagonal. You can see how it is passing. This is the fourth diagonal. This is the fifth diagonal, sixth, and this is the seventh. Now, if you follow the trend of how this thing is passing, so from the first diagonal, the only thing we have under that place is the 1s. We have 1s. Then the second diagonal, the only thing we have there is also 2s. Then the third diagonal, you start with a 2p, so you go with 2p, then followed by 3s. Then the fourth diagonal, it starts with 3p. That is 3p. Then you go to 4s. Then the fifth diagonal, you have 3d. Then you go to 4p. Then the next diagonal, that's where you have the 4d and you have the 4f. Now, as we have this thing now, this thing is actually in increasing orbital level. It is increasing in orbital level. So that implies that 1s is a lower energy level, is a lower orbital, is a lower energy orbital than 2s. So it's increasing, the energy orbitals, they are increasing from 1s to 4f. So according to Bohr's principle, it says we must fill each of these guys completely before we go to the next guy. So let's see what we were talking about earlier. So when we were doing the KLMN format, you could see the way it goes. We always fill this place, just 2 electrons, then we go to 8 electrons, we go to this. And I told you that M should be able to hold 18 electrons maximally. But whenever we are dealing with the first 20 elements, we only fill 8 electrons. We only fill 8 electrons maximally. Why is it so? This Bohr's principle is going to explain it to us. Let's pick the highest element in the first 20 elements. When I mean highest, I'm talking about in terms of atomic number. And that is what? With element with number 20. Element with number 20. So let's begin to fill these one after the other. Now, as I've explained earlier, the maximum number of electrons that can go in the any S subshell is 2. For P is 6, for D is 10, and for F is 14. So I want you to pay attention to that. Maybe I need to rewrite it here as well. Let me write it here. S can only hold 2. P can only hold 6 electrons maximally. and D can only hold 10, while F can only hold 14. So therefore, let's start filling one after the other. So S maximally can only hold 2 electrons. So we are done with 2. We are left with 18. Out of the 18, we have another S. This will take 2 only. So just 2. Then we are left with 16. Out of 16, this will take, P can take 6. So what do we have left? We have 10 left. And out of 10, this is another S. S can only take 2, so this will take 2. Then we have 8 left. P can take 6. So if you put a 6 here, what will be left here is 2. So 4S will take what? We take 2. So let's go back to this. If you go back to this, you realize that the 3M, the M subshell, sorry, the M shell rather, has this number of orbitals, 3s, 3p, and 3d. What I mean here is that, it has subshell 3s, 3p, and what? And 3d. Now, for the first 20 elements, you would notice that this guy has 3s filled. 3s was filled, 3p was filled, but 3d was not filled. And the total number of electrons that we say that maximally can fill the M shell, they are 18 in number. Why are they 18? They are 18 because 3s can hold 2. So we have 2 plus 3p can hold 6 maximally, 2 plus 6, and 3d can hold 10 maximally. So 2 plus 6 plus 10, that's going to be 18. So for the M shell, which has this coefficient of 3, they can hold 18 electrons maximally. And for the first 20 elements, according to Bohr's principle, we will not be able to get to the 3d orbital. So therefore, that is why we represent that maximally for the first 20 elements, the total maximum electron that can be in the M shell will just be 2 plus 6, which is what? Which is 8. That is why that restriction was placed for the M shell. So I believe that makes sense now. And this is how you write electronic configuration of elements. So all you have to do is arrange this. Once you master the way these things are written diagonally, then everything becomes very, very easy. You can ask any question that you want in the comments. I'm going to answer. I'm going to attend to everything all. So that's the Bohr's principle. Now that we have taken care of the Bohr's principle and also the way you write electronic configuration of any element, now let's talk about the On's rule. What is On's rule? On's rule basically tells us about how we place electrons in orbitals. Now, the s orbital, like I've explained earlier, it has just one orbital. Let me make this. Then the p, there are 3 orbitals. There are 3 orbitals. The d, there are 5 orbitals. 1, 2, 3, 4. So 1, 2, 3, 4, 5. Then we have the f orbitals. 3, 4, 5, 6. Don't mind my drawing anyways. So this S, P, D, F, these are the number of orbitals that they can have. And for the On's rule does not necessarily really affect the s orbital like that because it's only one orbital. But when you begin to go to the p orbital, the d orbital, and the likes, you realize that you have to fill the orbital singly before pairing. Now, what is pairing? Pairing is explained by the Pauli exclusion principle, which says that you can only have maximum of 2 electrons per orbital, and this guy must be of opposite spin. What does that mean? So for instance, if I want to fill electron in this place, there are 2 electrons that can hold in this particular orbital, the s orbital. So those 2 electrons, they are electron pair. And then, so for this place, we have 1 electron and we have 2 electrons. So I've paired 2 electrons in this place and I've made them have opposite spin. One is clockwise, one is anti-clockwise. Why do we do that? Is because electrons are negatively charged and like charges repel. So to prevent too much of repulsion, to prevent surge of energy, we put electrons in this orbital with opposite spins. Opposite spins. That's basically what Pauli exclusive principle states. So I've been able to touch the three principles of electronic configuration now. Now, let's say for instance, I want to fill like, let's say 5 electrons. You know, P can hold 6 electrons maximally. Now, let me make it 4 electrons actually. Let me make it 4 electrons. And because I've known that P can hold 6 electrons maximally, but I want to fill just 4 electrons in the P orbital, then I can decide to say, okay, 1, 2, 3, 4. If I do this, then I've disobeyed what we call Hund's rule, because what Hund's rule wants us to do is that it wants us to singly fill this orbital first before we start pairing. So what do I mean by that? I have 4 electrons I want to fill in the P orbital. So I'm going to do this first. 1, 2, 3. So once I've totally filled everything here singly, then I will now start pairing. So out of 4 electrons, I only have 1 left. So this will go there with an opposite spin. And this is the correct way. This way is wrong. That is basically what Andrew is talking about. So let's pick a random element and let's quickly see if we can draw the orbital structure. I'm going to go way down. Let's pick a random element. Let's say we want to pick... let's pick chlorine. Chlorine will suffice. So if we're picking chlorine, we know we have 17 electrons. So let's quickly write the electronic configuration. So according to Bohr's principle, we are going from 1s to 2s. Then if you go back to the diagonal, after 1s, 2s, the next thing you are going to have is your 2p, 2p, 3s, 3p. So we have 2p, 3s, then you have 3p, then followed by 4s, and followed by 3D. But we don't need 3D because we know that this is the first 20 elements, so this will suffice. So let's begin to take our electrons. S will take 2, S will take 2, P will take 6. So by now we have 10 already. We only have 7 remaining. For the 7, this will only take 2 as well. And then since we have, out of 7, 5 will be left here. So we have what? We have 5 in this place like that. So this will be the electronic configuration of chlorine. We do not need this 4s at all. So let's see. 2 plus 2 is 4. 4 plus 6 is 10. 10 plus 2 is 12. 12 plus 5 is 17. So that's okay. Now, so let's go now. The 1s. For the 1s, we have this. For the 2s, I think I should put it under. So let this be the 1s. This is going to be the 2s. This is going to be 2p. This is going to be 3s. And this is going to be 3p. So let's begin to fill our electrons one after the other. For the s, we have 2 electrons for the 1s. For the 2s, we also have 2 electrons. Those ones don't really have problem. For this p, we have 6 electrons. So we singly fill first. 1, 2, 3, then 4, 5, and 6. Then for the 3s, we have 1, 2. Now, we have 5 electrons to fill here. So the first thing we need to do is that we need to fill singly first. 1, 2, 3. Then we go 4 and 5. And with this now, we have been able to arrange electrons in the orbitals. We have been able to arrange electrons in the orbitals of the subshell and the subshell of the shell in chlorine atom. So this is what it looks like. And that's basically the summary of atomic structure and the electronic configuration. And this is for day 3. I know this is quite a longer class, but it's worth it, and I hope you have learned enough. Don't forget, if this actually makes sense to you, you should like, comment, and share with your friends as well. Let them know about the classes. Share them the registration link. Let them register. Let as many of your friends as possible. Let them know about these classes. And if you need any clarification on anything, you can always ask the question. I will attend to you. And I can even make a video if there is need to make any video clarification. And some of these videos, you need to watch them over and over and over and over again so that you can grab the whole concept better. I'll see you in the next one.